Okay, welcome to Photographic Technology Day number 9. Today we have guest lecturer Ben Lutch, did I get that right? Lutch, who's going to talk to us about astrophotography. Ben has a computer science degree from Stanford. He was one of the founders of Excite, and he comes to Google by way of JotSpot. Ben, take it away.
Thanks. All right, is this working? Everyone can hear me? Yeah. All right. So my talk is on astrophotography. And astrophotography is naturally the techniques you use to photograph things that are not on this planet. And it's also sort of one of the primary ways that we use to learn about the rest of the universe. So I like to do astrophotography because I like the pictures and I think they look pretty, but there's also sort of a vast amount of science you can do with it as well. So my first slide, if it comes up here, is an animation, which is currently not animating, but this is sort of a fisheye view of the sky. And what do you need to do to make an astrophotograph? The first thing you need to do is you need to compensate for the fact that you're doing sort of the ultimate pan. Right? You're on the Earth and you're taking these long exposures, 10, 20 minutes, and the Earth is moving. And so you have to make sure that your target stays inside your field of view the whole time. This can be very challenging. Not only does the Earth sort of, obviously move continuously, but the atmosphere will play tricks on how fast things appear to move. And there's also a lot of problems with trying to make sure all your equipment sort of follows the star as well. There's lots of little things that can happen where mirrors sag or tubes flex, things like that I'll talk about later. So you need long exposures. One thing I sort of like about this picture, and you can't tell so much from the animation, but when it's not animating it, but you can really kind of get the feeling that from seeing a big fisheye that you're really sort of someone on some planet that's sort of spinning out there, and you can see the galaxy. And so it gives sort of the feeling of the things I like about astrophotography. So the next slide is again a non-animating, it's supposed to animate picture of light pollution. This is supposed to be 3 slides of light pollution at different times in the United States. This is sort of a projection of what it's supposed to look like in 2025. And it's a little bit less now, but as you can see, there's a lot of light pollution. And light pollution makes astrophotography hard because all the light that goes up into the sky illuminates it and affects our ability to see faint things. Even if we stack exposures, if there's a certain amount of just light pollution in the sky, there's just stuff you can't see. This is also just bad from sort of a conservation perspective, right? This picture shows light that's not going on the ground. This light isn't really helping anyone. This light is just going up into space. So this is all totally wasted energy that's sort of diminishing this natural resource, which is the sky. And here's sort of a global view. This was taken by NASA. This is a mosaic. And you can kind of see in the United States, if you want to go find a place where there's a really dark sky to do some science or some good astrophotography, it's hard. You got to drive a ways. Same with Europe. So it's tough to actually find a good place to do astrophotography, and there's a whole sort of science behind finding good sites. If you read about how they choose to put or where they choose to put really large telescopes, there's a lot of thought that goes into it, and one of the biggest factors is a place where it's dark, but will stay dark, or place where they can put in light ordnance. I should also mention here, back on this slide, that this slide comes from the International Dark Sky Association. And the mission is to preserve and protect the nighttime environment and our heritage of dark skies through quality outdoor lighting. So they'll help you or your community find lighting fixtures that will sort of ensure all the light that you use sort of falls on the ground or falls on the things you need to light up and doesn't spill up into the sky. I don't know if you've driven down, I guess it's 580 or 680, seen all sort of the car sales places where just light is just sort of barfs out into the sky all the time. Okay, so the next thing you need is, oh, that doesn't look so good. The next thing you need is to realize that you're trying to image through the atmosphere, and the atmosphere is mildly refractive. So this actually shows a picture of Mars through an 8-inch telescope, and what you can't really tell is that Mars is sort of dancing and jumping around, and bits of it are coming in and out of focus. And it's not due to any sort of problems with the mount of the telescope. And this is actually captured with a webcam. And if you look at the PowerPoint, which I can post later, you'll actually see the animation's pretty smooth. And it's all due to seeing, right? So the atmosphere's pretty thick. It's, I don't know, a couple 100,000 feet thick. And it's mildly refractive, and it's moving around a lot, right? It's sort of compressing, and it's moving. And the net effect is you have this weak lens that's sort of moving over your image, and it blurs things. And so this is a huge problem for astronomy, because you want to make a really big telescope so you can gather a lot of light, but also so you can have very good resolution, right? As Ram was saying in the earlier lectures, so the bigger the aperture, the smaller your area disk, and the better you're able to resolve things. But if you have this atmosphere, this weak lens moving and blurring everything, it sets sort of a lower limit to your resolution. So the general rule of thumb is that after about 0.5 arc seconds, the atmosphere will sort of take over and will blur anything more than that. So you could have some massive telescope, and there are massive telescopes whose theoretical resolving power is, you know, 100th of a millisecond. Practically speaking, without playing tricks, the atmosphere will really sort of limit you to about half an arc second. Yeah.
It's not the same during the day and the night. If you were trying to get into the ground from above, you have the same kind of 0.5 arc second limit, or worse?
Thanks, Michael. I'm not really sure. I don't know why it wouldn't be the same. I know that a lot of the pioneering adaptive optics that were actually done by the military in the 70s in Maui on Mount Haleakala, and so I assume that it's the same. And actually, interestingly enough, the reason it was developed is because they wanted to be able to identify a satellite as it went up on its first orbit, and so they had all these sort of early adaptive optic systems to try to unblur the image. But the short answer is I'm not really sure, though I think so. And so in order to combat this, right, there's sort of a pretty big spectrum of things you can do to try to make your telescope perform optimally and achieve its optimal resolution. One is you can use a web camera, like I'm using here, and you can actually run a program through all the individual frames and look for the ones where your image is the roundest and you have the most high-frequency information. This means it's probably pretty sharp. And then you stack those up. I'll show some images at the end of the talk, some very, very impressive images of Saturn and Jupiter. And these are actually taken with sort of a normal Celestron telescope and a high-speed web camera. And the gentleman in Chris Go in the Philippines who takes these, runs these through a program and literally just pulls out, you know, 2/3 of the blurry images and just keeps the good ones. So the idea being that as you have sort of this blur that the atmosphere induces, there's also moments where things are pretty clear, pretty good, and you just sort of pull those frames out and you image many times per second. Yeah, right there. Uh-huh.
So that when the image flickered or deviated from this long time exposure, it wouldn't affect that flicker.
Okay, so he basically just it was sensitive enough that it would just sort of take only expose the things that were not moving, basically.
One of the things that matches long time.
Okay, oh, that's interesting. And so the modern equivalent is to use adaptive optics, and this is sort of what you'll find on any really large telescope now. And adaptive optics basically changes the surface of a mirror to account for the bending of the light by the atmosphere. So you can sort of imagine that you have some distant source, say in this case it's Mars, and the light is this sort of spherical waveform coming in, and it's bent a little bit by the atmosphere. So what ends up happening is that pieces of the waveform will hit your primary mirror at slightly different times. So they use a modified sort of Shack-Hartman sensor, and they can tell how the waveform is bent, and there's actually little pistons underneath the main mirror that deform it nearly in real time to basically zero out the effects of the atmosphere. And this way, a lot of these really large telescopes can try to zero out the blur from the atmosphere. Yeah. So that's a good question, and the question is how large of a frequency spectrum is that valid for? I'm not sure about the adaptive optic systems. I'm more familiar with there's a tip-tilt system, which is sort of basically just a mirror that tips and tilts and doesn't deform, and those typically are good at about 10 hertz. Faster than that, and they don't really end up working very well. So I'm not actually sure how fast the adaptive optics systems are changing. That's the question?
I was more interested in the optical frequency. So
Right. Yeah, I don't know. I know that the instruments they use, the sensors they use, definitely go from, you know, sort of deep infrared all the way through, I don't know, 900 nanometers or so. So I'm assuming that it works for that whole range, but I really don't know. Yeah. Yeah, that's right. So the question is, isn't there an image by a way that they can shoot a laser up into the ionosphere and watch its image wiggle and sort of use that as their guide? And they do that. I think it's a sodium laser. I'm not exactly sure how it works, but you can see pictures of giant observatories with this sort of finger of light sticking out. And the idea is to use that really bright with a lot of signal to noise source as it's right next to the target where you're moving, where you're looking, and observe the way it undulates and sort of use that to reverse your adaptive, the blur. That's also a nice technique because one of the problems you have with a huge telescope and a long focal length is that your field of view is really, really, really small. And you're often looking at things which are not in the plane of the galaxy, right? So you've got the galaxy and you're looking at something sort of up. You're looking at a distant quasar or something that's not sort of occluded by the dust in the galactic plane. And so it's really handy to have a bright star nearby. So you can actually kind of have a really good signal to noise and understand what's happening in the atmosphere and to be able to counteract it. And the further away from the galactic plane you are, the less probable you are to actually have a nice bright star there. So they do shoot this laser up that they can sort of track right next to their image. Okay, right. So what do you need for astrophotography? You need long focal length because stuff's far away, and you need a big aperture to gather light. This is sort of at the small end of things. These are 200 millimeter f1.8 lenses. The reason why I chose this picture is because there was some discussion on the PhotoTech board about these lenses. They're not made by Canon, but they're sort of over the shelf. You can get them on eBay lenses. And these are very good lenses and have a nice flat field. And this particular program is interesting because it does a survey of the night sky. There's these sort of copper little ingots are actually weights where they're going to put more of these cameras. And what this does is this looks for extrasolar planets. And what it does is it takes frames of just massive number of stars every night, and it looks for minute changes in their brightness. And it looks for periodic changes in their brightness, which correspond to a planet. It's got to be pretty large, Jupiter size, that actually passes in front of a star. So you can imagine you're looking at a star, you can measure its brightness very accurately because you've got a very linear CCD. And as the planet passes in front, it essentially sort of eclipses some of the star's light. And we'll do this periodically, and you can measure some things about the extrasolar planet that way. As you can see, there's not a conventional camera on the back of there. These are special cameras. These are, I believe, 2,000 by 2,000 pixel back-thinned. I don't know who makes a sensor, but they're 13.5 micron sensors, and they're cooled to like -50 degrees, and I'll talk about the cooling in a moment. And you can also see that sort of a Y-shaped mount. It's not coming up very well on the slide, but these are all sort of set on a mount that I'll talk about in a minute that tracks the sky very accurately.
I'm surprised, not knowing much about this, that you don't use longer lenses.
Right. Well, first, so the question was, you know, why would you use a longer lens for this? And the reason is because the longer the lens is, typically the longer the focal length, the smaller field of view. So if you really want to cover a lot of ground, you need a pretty wide field of view. So you need a shorter focal length lens or a bigger detector. So since there's sort of a practical limit on how big of a detector you can have, you try to get shorter focal length as possible with enough sampling, enough sort of pixels per arc second of sky that you can really do the science you need to. And it turns out for their purposes that this is sufficient. It gives a very wide field of view. They say sometimes there's 50,000 stars on a 1-minute exposure. And they can measure the magnitudes of all those stars accurately enough for their science.
What does back-thinned mean?
So back-thinned has to do with the way that the CCD is built. So there's two ways of which I'm aware to make CCDs. One is the normal Kodak, well, not normal, but the Kodak CCDs have the face of the CCD, and then there's pixels on it. But on the face of the CCD as well, there's the electronics, so the little gates that suck out the electrons so you can do your reading of them. Now, these gates take up some of the surface area, excuse me, and they lower the quantum efficiency because your pixel has a certain amount of area, but for that piece of area, there's a little bit of stuff on there that has to read it out. Back-thinned is actually when you take a chip like that and then you flip it over and you thin it. They sort of thin it by etching it, so it's extremely thin. And then what happens is you're actually able to get a much higher QE because you're not blocking any of the photons. With the front illuminated ones, they actually have what are called micro lenses now. So they have an array of very small lenses which essentially kind of are over the part of the gate structure that might otherwise block a photon. A little lens sort of directs that light into the well, and that boosts the QE by about 10 or 15% on these. The problem with the back illuminated is just they're harder to make because they have to be very flat and precise. And typically they have a smaller well depth, so you can fit fewer electrons in there, which can be disadvantageous in some applications. Okay, so from the small lens to the very large, this is the Keck primary. Excuse me. This has a 10-meter primary mirror. It's the largest one in the world. There's a couple different light paths. F25 is the longest, so it's 250 meters of focal length. So you can imagine you need a very steady mount and some good adaptive optics to make sure things don't wiggle around. This also has the advantage of being on Mauna Kea, which is 14,000 feet in the middle of the Pacific, with a very sort of laminar airflow, which is sort of polite to the seeing. Actually, the way this one was made was kind of interesting. The 10-meter mirror is actually made of, I think it's 36 hexagonal segments. And the mirror is parabolic, so there's no spherical aberration. And in order to make all these segments the correct shape, this guy, Jerry Nelson, I think he's at Santa Cruz right now, took the hexagonal segments and then stressed them. And he figured out how much you can kind of stress the glass and then make sort of a very easy spherical polish to it. And then when you let go of it, it kind of snap back into a parabolic shape, and then you can fit them all together. This is the only really large one I know of that's made that way. There's actually the Keck twins. There's two of these side by side. Other large mirrors are actually made by what's called spin casting, which is kind of an interesting technique which was inspired by spinning mercury around. It used to be that to make a really large mirror, sometimes people would just take a big sort of dish of mercury and just spin it around. It had the disadvantage that you couldn't really move it very much, but you could do time delay integration and some interesting astronomy with it as well. Anyhow, the spin casting is you basically heat up the glass and you spin it, and it gets pretty close to the shape you need. You need to do a little polishing, but it's an easy way to get most of the way there. Okay, so that's the Keck. And you need a mount. So I'm pointing out the mounts on a couple of the other setups. This is a more modest mount. This mount is made by an American company called Astrophysics. And having a very stable tracking mount is really, really, really important. People often say that you should spend sort of at least as much on your mount as you do on your telescope. This mount is a robotic mount, so you can kind of program it, hook it into your planetarium programs. It tracks the sky very accurately to within 5 arc seconds of periodic error. So that means that if you have a star that's not moving at all and you polar align your mount perfectly, the star will wiggle under sort of 5 arc seconds based on sort of the mechanical vagaries of the mount. That being said, 5 arc seconds isn't going to be enough, right? If you know that the atmosphere limits you to about half an arc second, you're going to have to improve on that. And there's a bunch of ways to improve on that. But it turns out that's a really good start, 5 arc seconds. Okay, and the other thing you'll need, of course, for astrophotography is a camera. This is the camera I'm going to use for my examples later on. This camera is made by a company in Santa Barbara Instrument Group. And this uses a KAI 11,000 CCD. This is 11 megapixel, full frame, 36 by 24 millimeter CCD with 9 micron pixels. It's cooled. You can cool it up to maybe 30 degrees Celsius. There's a desiccant in here to keep the chamber nice and cool, to keep it nice and dry. So when you cool it off, you don't have dew forming and frost forming on the inside of the mirror, of the window. The shutter you can see is not very sophisticated. When you're taking a 20-minute exposure, you don't need a very sophisticated shutter. This is just a little thing that kind of spins around. What you can't see in here is, or you can barely see, is Cheryl fire up the laser here. Right here, there's actually a little prism that is a pick-off prism. And what it does is it takes a bit of starlight and it shoots it off to the side where there's a very small CCD that can be read out very frequently, independent of the big one. And this is used for auto-guiding. What auto-guiding is it's a way of trying to overcome some of the issues with the mount not being as precise as it needs to be. So what happens is, as you're taking a long exposure with a big chip, you can place a star, and this is particularly easy with a wider field of view. It's harder when you have fewer choices of stars with a narrow field of view. But you find what's called a guide star, and you place it on that secondary CCD right here, sticking off to the side. Then what you do is you read out the centroid of that star, every couple seconds or half second. And as the centroid of the star moves, you can send a pulse to your mount to correct for the drift that's taken place. So you can imagine that due to refraction of the atmosphere, or maybe you're not aligned correctly, there's going to be some drift over a 20-minute exposure. And so what you can do is every second or two, you can send a little minute pulse to the mount to overcome that. Now, it's a pretty good way of getting stuff, less than 3,000 millimeters to keep things really well centered. But you'll realize it's sort of a reactive thing. You'll have noticed that the star has moved, and you will sort of move it back. And you're also sort of moving this pretty big moment arm. You can imagine you have a telescope, and you have to sort of wiggle the whole thing around to overcome whatever drift you've noticed. So while it's a pretty good solution for most sort of amateur, up to, I don't know, 3-4 meters. If you go further, if you have a longer focal length than that and you're magnifying more, you're going to need a slightly better solution. But this actually turns out to be really good. And these are you can get these off the shelf, and they're actually less expensive than you think. Oh, and I should mention too that the sensor is monochrome. It's very rare that you find a color sensor, just because the QE is so affected by having that Bayer filter. Do you have a question? So the question is it possible to use a piezo server on the CCD itself? The answer is sort of. So there's a little tip-tilt thing you can use. This same company makes a mirror that goes into the light path. It's sort of a little diagonal mirror, and it has little speaker coils on it. And you can use that. And it's not really adaptive optics, but it can go maybe 10, 15 hertz, and it can actually do a lot more in terms of keeping the star on the image without having to move the whole telescope, and it can be read at a higher rate. Did that answer your question? Cool. And then you'll need your filters. Since we're using a monochrome sensor for the QE, and also you want a monochrome sensor because often you'll want to do some narrowband imaging, and it's hard to get a sort of a color sensor that's really very that doesn't have some weird cutoffs in places where you might want it. So it's nice just to have the monochrome sensor. Typically, what you'll find, at least for amateurs, is an RGB-L filter set, a little filter wheel, and you can see the red, green, blue in there, and the clear one, the reason why there's a clear filter, there's two reasons. One is they're typically made so they're parfocal, so you can switch filters around without having to focus. And the other is that often the clear filters are coated, so that when you look at sort of the bandpass of all of the sort of the sum of the bandpass, or the intersection of the bandpass of your RGB filters, you want to sort of cut off your luminance at the ends of that. So the monochrome sensor is sensitive sort of past, nowhere, I don't know. It's got a little sensitivity up. We'll see the QE in a second. But it's got sensitivity past where you'd want it to make a normal RGB picture. So sometimes if you're making just a pretty picture, you want to actually kind of cut things off right after your red and blue filters tail off. You can also put in narrowband filters. So I have a picture a little later where there's a hydrogen alpha narrowband. It's a 6 nanometer band pass. The spike sort of at 6 nanometers. The spike is, the width is about 6 nanometers. And the narrowband stuff is nice because it cuts out a lot of the sky noise. You can pick a band that, there's a lot of emission in the sky, but street lights, don't emit, in that range. So while you're cutting out on a lot of the light that you let in, you're cutting out even more drastically on the light that you don't want. So you can get some nice contrasty shots with them. Okay, so know your sensors. So the first thing you really want to do when you start doing astrophotography is you want to profile your sensor and know it really, really well. At Keck, they have sensors that they essentially sort of run this whole profile on almost every time they fire up the camera. They have sort of overscan, and they check the bias and all this sort of stuff, which as a sort of an amateur, I don't do as often, but it's important to know this stuff. So this is the QE curve for the camera I was talking about, for the KI 11000 based camera. You can see it peaks here at about 50% QE at 500 nanometers. So what that means, of course, is that for every 2 photons, you kind of get one electron. You get basically 1 electron out of it. And you can see again, it's sort of sensitive. Your QE is still 5% up here at 900 nanometers. So if you're trying to make a balanced color image, that light can be problematic because either There's no way to sort of account for it in your RGB. Or if you're using a telescope that has any refractive elements, chances are it's only corrected in the visual, right? Only corrected between 450 and 700. And so you may actually find out that you have some sort of fuzzy-looking stars because your sensor is actually sensitive to the defocused part of the spectrum where your refractive elements simply haven't been tuned to focus. Not a problem with reflecting telescopes, which is why all essentially big professional telescopes are reflecting. You don't have to worry about chromatic aberration. So mine, I think I mentioned, has about 9 electrons of readout noise. Electrons per ADU is the gain, so 0.8. So 0.8 electrons end up being sort of one count, and the full well depth is about 50,000 electrons. And knowing the full well depth is good because the cameras become nonlinear and do funny things depending on whether they have anti-blooming or non-anti-blooming sensors. So it's nice to understand your full well depth and how much light you need to stay in the linear range. As you get in the nonlinear range, first of all, it's bad for doing science because you can't measure magnitudes and things like that accurately. And also, it's hard to balance your color because you're going to have clipped one of your color channels. Okay, so another part of having so we're going to talk about how you would process an astrophoto. And the first thing you need is make sure that your setup is fully tuned and working. That's sort of one line to a year's worth of work. So the first thing you want to make sure is that your mount is perfectly polar aligned with the axis of the Earth. In other words, as your mount is rotating, it needs to rotate at the exact same rate that the Earth is, but it also needs to be aligned with the North Pole. And there are a number of ways to do this. Probably the best way is to actually set up your mount, get a pretty close bead on where you think north is, and then actually put a star on your sensor and read it out. And your star will drift. Put some crosshairs on it, and your star will drift based on how much you're misaligned. And you can sort of continuously tune your mount over the course of 10, 20, 30 minutes. So you can zero out that drift. And essentially, the star may move a little bit back and forth due to periodic error with the gears or due to seeing, but if you can kind of get it to stay in the same place for a chunk of time, then you're very well polar aligned. So over here on the right, I have a screenshot from this program called PemPro by a fellow who lives around here, actually, named Ray Graylack. And what this does is this actually profiles the mechanical error in your mount. So what happens is, the error is usually pretty predictable. It's sort of a mechanical system, and you can sort of roll through your gears a few times. And you can graph out, and you can say, all right, how much does a star move based on sort of the mechanical error? And it sort of smooths it out. And then what it does is this program will program your mount, and then your mount will know where it is on the worm cycle. And then it will sort of proactively play back pulses. So for instance, right here, it can say, oh, I know I'm too much in one direction, so I'm going to play back a little pulse to the mount to counteract that. And this can account for a lot of that 5 arc seconds. So you can really profile your mount. You can see the mount here, this mount's starting out at, +3, -4.6. And you can smooth it out to, I don't know, half an arc second in either direction, just by doing this periodic error. This is nice too, right, because this isn't reactive. You're not looking at a star in your sensor in your readout that's moved and then trying to move the whole mount accordingly. You actually sort of know where you are in the cycle, and you can try to account for it. So this is sort of one of the many things you can do to tune your setup. Also, I mentioned T-point here. T-point is also used by sort of big professional observatories, and this actually sort of profiles a little bit of the things that I was talking about earlier, where there's for instance, there's flexure in your system. If you have a really long telescope, particularly the older telescopes, the older refractors, where you had a giant lens kind of 40 feet in the air, and there's a lot of kind of bending and sort of wheezing of old things going on. And it's important to be able to point very accurately, especially when you have a very long focal length and your field of view is very small. So T-point actually can profile. T-point is sort of made to profile your pointing. So you basically point all over the sky. It sees how much things are off, and it makes a very complicated mechanical model, and then sort of corrects for the pointing errors that you might have, and does a really good job of making sure that no matter where you point in the sky, your target's going to be dead on. The next thing is focus. So focus doesn't sound like a really hard problem, but focus with a telescope is really sort of the bane of a photographer's existence. It's really hard to do perfectly, and there's not much tolerance for having anything defocused. And the reason is because you're working sort of at the very limit of your resolution. Any lack of focus will sort of rob you of all the sort of high frequency details, the things that make an image good or scientifically interesting for the most part. So there's a really interesting program which a lot of people use to to focus. And it's called Focus Max here, and it interacts with your CCD control program. And what you do is you essentially profile the size of a defocused star and understand what that looks like in your optical system. And then you move your sort of automated focuser the correct amount. So what you do is, first of all, you have to understand what the full width half maximum measurement is. This is just sort of a way to measure a pulse. And it's the, you measure the width at the half maximum, right? So here's the maximum, half maximum, and then you just sort of measure this. And so what you do is you go through and you take a star that's defocused and you move through focus. Now you probably know just intuitively, if you put a camera on a light and then kind of move in and out of focus, the light will get really big when it's out of focus, then it'll go down to its sort of minimum size, and then it'll pass through focus again. And on the other side of focus, the defocused image will increase in size. So, what Focus Max does is it essentially profiles that. It moves your focuser a predictable amount, and it looks at the size of the defocused image. And then it can, and you do a bunch of these. You run through a bunch of these graphs, and you can actually understand, okay, this right here, this line, this is where I'm perfectly focused. And so you can really sort of characterize your optical system, and then when you look at a defocused star, all you need to do is know what side of focus you're on. And then the focuser can say, okay, well, I know that's 17 steps or however many steps from perfect focus, and it can crank it back. This is really useful because there's a lot of metal in telescopes. They contract and shrink a lot with heat. And whenever you change filters, particularly with the fast optical system, your focus changes as well. So it's really nice to have this automated method. And in fact, there's even more complicated programs that will move your telescope slightly so that you always have a bright star to focus on. So for instance, suppose you're making 20 exposures of a very faint galaxy, and there's no bright stars around there on which to really focus. You can sort of program your control program to actually slew a little bit to a bright star, focus on it, take an exposure, slew back, focus. And sort of continually focusing doesn't take very long, but it really ensures that you don't lose any 20-minute frames, right, which are pretty valuable to blur.
So you mean like in the middle of your exposure, you take a picture of something else?
Right, so it's not, so the question is, in the middle of exposure, do you take a picture of something else? So you're kind of locked in for the length of the exposure. There's actually some stuff you can do to actually tune the focus during the exposure itself, but typically, 20, 30 minutes isn't quite enough to really ruin things. So if you focus at the beginning of an exposure and then focus again for the next, every time you take an exposure, if you focus at the beginning, turns out that's usually sufficient. There are some temperature sensing things that you can put on your telescope, which you can train, which will adjust the focus continuously throughout the exposure as well. To answer your question.
Well, I didn't understand what you meant by with the big star. But
Oh, so I'm saying that sometimes if you have a field of view, a picture of something you're taking that's very faint, there's nothing really to focus on. Maybe there's a fuzzy galaxy and there's no actually well-resolved star, and you need some reasonable signal to noise to be able to actually focus. So, so you can actually, after you're done taking a picture of this fuzzy object, you can actually move the telescope a little bit and then take something bright and focus on that, and then move back to your object in between. Yeah, right, exactly. Okay, and then I'm kind of glossing over a lot of sort of big points here, but you have to get your planetarium software working, which means that the software on your computer has to understand where your mount is pointing. CCD control software, which controls the temperature and interacts with all these other automated things I've mentioned, like the focuser, interacts with the planetarium program. Focus control, so get that all configured, and then we have to get the guiding done. Guiding's pretty hard too. This is just, I took this shot last night. You can see that I'm guiding on, you can't see the guide star, but this is a 700-second frame. It's M100, and you can see that, well, maybe you can't, but these are about 0.2 pixels of guiding error. So I'm barely guiding. So if you have things really well aligned and your mount really well tuned, you don't really have to nudge stuff that much to really sort of have things stay spot on. But it's important to get a sharp image. And the way that you set up your guiding is you actually put a star on your sensor, and then you send a little pulse sort of to each axis, and you sort of measure how much it moves. And then you sort of understand how much pulse you need to get the mount to move what distance. And then as you see things drift, you can, based on that calibration, you can send sort of the opposite pulse to the mount to make sure that, that the star, your object, stays exactly centered. Yeah?
So for the mount, the example that you gave, what is the typical typical resolution of a step in terms of pixel or percentage of pixel movement?
Sorry.
You were quoting, for instance, 0.2 pixel.
Right.
Correct.
Right.
I just wondered what the resolution was for individual pulse requests going to the mount.
It depends a lot on the mount. I don't know the minimum width. I did at one point.
But you target sub-pixel, like 1/10 of a pixel, or?
Yeah, I mean, there's a point, right, at which if you're sending these little tiny pulses, it doesn't move things at all. And I don't know the minimum, but it's sort of on the order of 1/10 of a pixel or less. Well, I guess the accurate response is it depends on the focal length at which you're working, right? Because if you're working at a really long focal length, it could be a so it's really arc seconds per pixel is really sort of the measurement. But still don't know the answer to your question. So. Okay, so processing an astrophoto. In order to do a good job processing an astrophoto, you're going to need to make 3 calibration frames: a dark master, which sounds evil, but it's not; a bias master, and a flat master. And then, of course, we'll need our signal frames, which are the frames of the actual object that we're interested in, and any color frames as well. So what's in an ADU? This was sort of covered in earlier phototech sessions, but in the case of an astronomical camera, there's this thing called bias. And what bias is it's just a count that's added when you start reading out your sensor. So you start out with 100. And the reason why they do that is just because they don't want to go negative and use up some of their bits, their A to D bits, using signed, worry about negative stuff. So they say, okay, say the sensor has 100 to read out everywhere. And the reason is because the noise, you get shot noise from the readout, and the noise can kind of go in either direction. So you just want to make sure that you have sort of enough of a little buffer so that you never actually go negative and have to worry about using up the signed bits. But you want to understand what your bias is, and you can either sort of take the manufacturer's word for it, or you can measure it. Dark current, which is a relatively predictable thermal signal. Readout noise, which is just noise you get that you can't do much about from the actual actor reading out the sensor, and then the signal. So dark frames. Dark frames are pretty interesting. People say it's dark noise sometimes, but I don't really think it's noise. It's actually a predictable signal. So here we have a graph of temperature versus dark current. So the first thing to understand about dark current is sort of what it is. You can imagine a lattice of silicon atoms, and they're sort of jiggling around. And if they're hot, right, they're jiggling pretty fast, and if they're pretty cold, they're jiggling much more slowly. And when jiggling atoms bump into each other, there's a chance that they'll knock an electron loose that'll get sucked into the well of the pixel. Now, there's no way of distinguishing that electron from an electron that's produced from a photon coming in from the sky and hitting the sensor. So, as you can see, the quicker you're jiggling your atoms, your silicon atoms, the more probability there is that you're going to be generating sort of erroneous signal, right? You're going to be dropping electrons into the well just because atoms happen to collide. So you want to cool your sensors. Big observatory cameras take this to an extreme. They use these dewars with liquid hydrogen in them, and they really cool the sensor as much as they possibly can. But as you can see with the sensor that I'm using in my example, after about minus 22 degrees, there's not a lot of gain to be had by cooling your sensor more, and it takes a lot of energy, particularly if you have a portable setup. You don't want to be draining your batteries cooling things off. And so the axes here are degrees Celsius, and the dark current in electrons per pixels per second. In other words, how many electrons would you expect to accumulate in a well in a pixel in any given second based on the heat? So the short answer is just sort of cool your sensor as much as possible. And you want to subtract this away from your light frames, right? So you've got a frame with some galaxy on it that you're interested in imaging, and you've got this other count too, which just comes from dark current. You want to know what that dark current count is so you can subtract it away. So you're just left with the signal that you're interested in. So what you can do is you basically profile the dark signature of your camera. Each pixel will accumulate dark current at a different rate. And so you can take a bunch of these dark frames. You get the sensor to be the same temperature as it would be when you're actually taking your photos. And you take a picture that's the same length of your photos, but you take it with a thing covered, right, with a shutter over it, and you're just accumulating dark current. Do that a bunch of times and average them up. And as you average them up, your signal to noise increases, right? Your signal increases more than your noise, and but net you have a more signal to noise, and you have sort of a smoother, more efficient dark frame. And then you subtract the master dark from each light frame, pixel by pixel, and you're just left with the readout noise and the signal, basically, after you calibrate all your light frames. Yeah.
So the assumption here is that it varies from pixel to pixel?
Yeah, and you find that does. There are things called hot pixels, which, for whatever reason, maybe there's a bunch of, silicon atoms closer together and they happen to bump into each other more. But you can definitely see that there's a variation. And in fact, another reason you need to do it is if you have a big sensor that takes a while to read out. So CCD sensors for astronomy are typically read very slowly, because the slower you read them, the less noise there is. And so you can actually see a gradient where the ones you read at the bottom have accumulated fewer dark pixels than the one you get to 30 seconds later as you finish reading the array. Okay, bias frames are just this added into readout. It's not signal. Often, and so the manufacturers just sort of pick a number. They just sort of add it to every count. So you can calculate it if you want to, or you can just subtract 100. Many people just sort of subtract 100 because it's sort of programmed in there in the electronics by the manufacturer. Flat frames. So flat frames are really interesting because they can really help to fight a lot of the problems that you might find in your imaging train. So let me talk about how you acquire them first, and then it'll make a little more sense about what they are. So the ideal goal in making a flat frame is to uniformly illuminate each pixel. So for every pixel in your array, you want to be outside of your sensor and outside, and you want to make sure all the photons go through your entire imaging train and send the same number of pixels out in a very flat way. It's going to be hard because finding a really, really, really uniform source of light is actually harder than you think. It turns out that the twilight sky is a pretty good source, particularly if you don't have a very wide field. If you have a narrow field, a few degrees off twilight right after the sunset is pretty uniform, and it also has the advantage that it has sort of the same spectral response as, or close to the same spectral response as the night sky. So you have a pretty representative flat frame. Some observatories just sort of paint a reflective white on the inside of their dome. Some people have like boxes that have a bunch of little lights in there and some diffusers, and you sort of clap those on the end of your telescope. So you make sure your light source is very flat, very uniform. You take a bunch of these flat frames. You want to get good signal to noise. So you want about 2/3 well depth, where you're still in the linear range of the sensor. And you want to normalize these, right? Because if one flat frame has a lot more, well, I guess, yeah, I mean, it's ideally you normalize these so they all sort of have the same weight. And then you average them up. And what you end up with is sort of a signature of what happens to flat light as it goes through your system. So if there's vignetting in your system, you'll see vignetting on the flat frame. If there's dust in your system, you'll see a dust mode on your flat frame. And then what you can do is you basically divide your resulting signal image by the flat frame, and it boosts or sort of retards the signal in each pixel based on whatever issues there might be in your optical system, or even QE changes between pixels. For instance, one pixel might just be less sensitive than another. You want to sort of boost them up so that were your light source uniform, your result will be uniform. And I'll kind of give an example which you can see, which makes a little more sense. So it takes care of vignetting. And you can do this actually on terrestrial photos too. So the parts that are dark, it makes them lighter. If you have dust on your cover slip, which is very often the case, you can, it's sort of the shadow, you can sort of multiply by the inverse of your shadow, and it boosts up the darkness where the shadow would be. Pixel to pixel QE inconsistencies. And it's sort of critical for scientific astrophotography because you can be fooled in thinking that, hey, this star is dimmer, maybe there's something going in front of it, where, well, it was just a piece of crud on your sensor. So you can actually, like I said, you can also try flat framing terrestrial photos, because I'm sure you guys have all seen that if you have a very fast optical system, the corners are dark from your vignetting. Okay, I'm going to start hurrying a little bit because we're almost out of time. So signal frames. This is just the signal from the actual image that you're taking, and the basic story here is that signal adds and noise adds with the square root of signal. So up to a point, if you keep adding more exposures and stacking them up, you'll just keep getting more signal, and it goes up by the square root. Now, there's a couple things you can do too, which actually help make your frames better. And one thing is dithering, which I mentioned a frame back. And dithering is when you take an exposure of an object. What you can do in your next exposure is move the telescope very slightly so that when you combine or average your frames together, any correlated noise that's because of the sensor will get averaged away. Now you can imagine there'd be some, some funny spot on the sensor that's a little more or less sensitive, and a lot of your flat frames should take care of that. But there's a lot of correlated readout noise and things like that, so that if you actually kind of move your sensor around a little bit and then sort of average your images, stack them all up, align them and stack them, you'll actually end up smashing down a lot of the correlated noise on your sensor. So the takeaway from this is take a lot. So the more signal you get, the more you stack it, the smoother your image is, and the higher signal to noise. And this is sort of what you get if you stack a lot of signal. So this is actually an interesting photo. This is taken by a gentleman in, I believe he lives in Texas, named Russ Chrome, who takes fantastic astrophotos. He has a remote observatory in New Mexico. And you can see here he spent 28.5 hours of exposure. And by example, the Hubble Deep Field was 42 hours of exposure. And you can also see here that he combined both some narrowband filters with some more broadband filters and even a luminance frame. And you can do this because no one really knows what the color of stuff is in space, right? If you go out and look at a nebula with your naked eye, it's green because that's the only place you're sort of sensitive enough to see it because it's faint. And even if you were to rush right up to it, the amount of light per sort of square foot still would prevent you from seeing any color. So a lot of the color is sort of an interpretation or sort of maybe scientifically correct over whatever set of wavelengths you want to represent color. But it's really up to you if you're trying to show something or show a structure, sort of combine whatever sort of set of exposures and wavelengths you want. And so here, you know, there's a lot of very interesting stuff going on in these narrowband ranges, and those are sort of used as part of the luminance to bring up the contrast of the picture. And this shows what I was referring to earlier about the flat frame. This is the Super WASP program with these Canon lenses. And the reason why this is a good example is because those Canon lenses were really fast. They were f1.8. So you can see there's a lot of vignetting up here. This is your raw image. You see there's a bright spot in the center, as you'd imagine. Here's your flat field. As you can see, it shows the vignetting. And when you divide through by your flat field, the field's flat. So all the stuff, the dark stuff has been boosted. Your bias, as you can imagine, is pretty uniform. And the dark current, you can see here, maybe it looks like there's some heat generated here by an amplifier off chip, and it's warming things up a little bit. That's typically what you'd see from that. So, so the dark frame is removing all the additionally accumulated dark current from that warm piece on the chip, or off chip, I should say. So here's your final image, which is nice and flat. It looks like a sort of nice, healthy star field. Combining color frames. So this is sort of analogous to doing a white balance. You have your R, G, B, and maybe L, and what you want. And the reason why I put this Hertzsprung-Russell diagram up here was to show you that there are some white stars, and there's a lot of white stars, and you can actually just find a white star somewhere that's near your target, defocus it a little bit, and you can actually use that to white balance your R, G, and B frames together. You have to make sure, again, not to clip these too much, because if you do, your color will be skewed, right? If your luminance is clipped or your RGB is clipped, you're going to get funny colors. And it's very often when people start doing astrophotography, they're like, well, why does my thing look like pink or orange or yellow? And it's because they were like, oh, I need a bunch of signal, so they stacked things up, and they ended up clipping one or two or all of their channels. So this is an image of a bandpass filter, of the set of the bandpass filters that you might use. So here's the blue, the green is a little more spiky here, and the red. And the takeaway from this is really that these filters are designed so that some of the wavelengths in the universe which are most common are passed. So hydrogen alpha, that's a big one, oxygen 3, and that's sort of at the intersection of these. And so there's a lot of care taken into the design of filters to make sure that you cover the whole range, but you also don't have some emission sort of where your filters cross. Okay, so what do you get? This is a somewhat washed out picture. This is the Horsehead Nebula in Orion. This is a really wide frame. This is taken with that example camera. And this is a 6 nanometer bandpass hydrogen alpha filter. This is a very pretty thin filter, and it needed 20 hours of exposure because they're not letting in very much light with that narrow bandpass. And the camera's cooled to -22 degrees. So this image is really interesting. You can't see this galaxy very well here, but it's interesting for a couple of reasons. First of all, the resolution between these 4 little dots is really, the distance is very, very small. This is extremely high resolution. This is taken by a fellow named Roland Christen, who makes mounts and telescopes and runs astrophysics. He's a neat guy. And he took this photo as well. And this actually shows gravitational lensing. These 4 bright spots are actually the image of a quasar that's directly behind this fuzzy galaxy. And what's happening is the light is getting bent by the massive galaxy and coming back around through the other side. So this is the sort of the lensing that Einstein predicted. That's why it's called Einstein's cross, because there's 4 images of the quasar that are behind the galaxy that you can actually see from in front of it. And it's a pretty impressive accomplishment for such a small instrument. And this is a animation here. This is the fellow I was referring to earlier, Chris Go. And you can see these shadows here on Jupiter's surface. This is a transit, a double transit. 2 of its satellites are crossing past its face. And this is sort of a off-the-shelf 11-inch telescope, and he's using a high-speed web camera, monochrome with a color filter wheel. He's taken 1,000, however many thousand shots, and he's pitching most of them, just keeping the clear ones. He also happens to live in the Philippines, in Cebu City, where he's discovered that the seeing is very good. He also coincidentally discovered Red Junior, this white spot on Jupiter that turned red. With sort of a lot of interest in the astronomical community, and he was the guy who first noticed it, because every night he sort of rolls his stuff out and takes these amazing images. And this is another image by Russ Chrome. This is M51, and this is kind of cool. You can see how a lot of these stars have been sort of flung out into space by the collision of these 2 galaxies. And again, this is from his 20-inch telescope in New Mexico. And this is the last picture. This is taken by a gentleman in New York named Alan Friedman, who is using a very narrow bandpass hydrogen alpha filter again, but this time on the sun. And this is the solar chromosphere. You can see some activity happen here around this dark spot. So we're almost out of time. Like we are out of time. Any questions? Dick?
Say a word or 2 about the site where you've got a telescope.
Oh, sure. So I have my telescope set up at this place called New Mexico Skies, which is a remote observatory. And they host a bunch of telescopes there. There's, I don't know, 30 maybe telescopes. And some schools and some individuals have telescopes there. And what they do is there's some people who are very knowledgeable who maintain your telescope, essentially. This fellow named Mike Rice, who's a whiz, just sets up your whole system. You can kind of set it up at home and tune it, ship it out to him, and and ship it out with a computer. He'll essentially kind of throw a DSL line to your computer, and if you're well enough versed in all this software, you can actually sort of just fire it up on any clear night. There's a little weather console. Any clear night from my home, I can use all the stuff that I sort of mentioned here, but totally remotely. There's no real reason to be in front of your scope. This is all controlled with software and cameras and stuff. So there's no once your mount is set up, there's really no need to physically be touching it. It's nice to be with your equipment sometimes, but it's even nicer to have it sort of set up. So yeah, so on most clear nights in New Mexico, I have a little image. I have a little, little VM, a little, window of my setup down there where I'm controlling it and taking photos as well. Yeah.
So that 20-hour photo, how many nights was that?
So the question is, a 20-hour photo, how many nights was that? That was about over 6 nights, and it'll vary a lot based on how low you want to let your target get, or a lot of stuff. But so the one that I took was over about a week. Sometimes people take stuff over the course of a couple of years. They just sort of keep adding to it, right? And one guy, Rob Gendler, is sort of notorious. I don't know if that's the right word, but he'll take stuff with different focal lengths over the course of years and just sort of smash them all together once they're calibrated and bring up the signal to noise. Yeah.
Are there any adaptive optics available to the amateur?
So the question is, are there any adaptive optics available to the amateur? Well, there's that tip-tilt thing that I was talking about, which isn't really adaptive optics. There used to be one, a guy named Don Parker, I believe, who made an on-axis AO system, which is really just for planets, but it's not available anymore. So the short answer is no, but the long answer is I hope so. And people have sort of been working on different ways to do it cheaply. Yeah.
It seemed like you had a system which spent a lot of effort in individual pieces of the pipeline, tuning out error or accounting for issues either in the physics or the optics.
Right.
does anybody build the global model and then do global end-to-end optimization where, for instance, you use the fact that your stepper motors have certain characteristics to actually induce the dithering that you would then be picking up and account?
Yeah, that's a great question. So the question is, are there any sort of programs that do a lot of the end-to-end tuning, since all the individual components seem to require so much sort of care and precision? And the answer is yes. There's a couple out there. And what they tend to do is they'll take sort of exactly as you described, the end-to-end. You need to really get things set up pretty well first. There's no shortcut to like sitting in front of your scope and get everything tuned and balanced perfectly. But once you do, there's a bunch of programs that will, you kind of say, I want to use this target and I want it to focus every 5 minutes and do a bunch of color filters and wake me if it gets cloudy, kind of thing. So there are a few now that do that. Any other questions? All right.
Before we finish up, Sam Roes wants to say a few words about some astronomy stuff he's working on. Thanks a lot, Ben. Appreciate the talk.
I just want to take 1 minute. Thanks. I just want to take 1 minute to tell you about my 20% project, which is a project, it won't help you take a photo, but if you have a photo, oh, you want me to use this? Okay. If you have a photo, it will help you find exactly where it is on the sky. Do you have a web browser, Ben? I'll let you do it. Anyway, Chris Ulick, who is here, and I see Lance at the back. These guys know about this project, but if you just find me in MoMA, Roweis, R-O-W-E-I-S, if you're interested in amateur astronomy and locating your photos, yeah, we can put a link. But I'll show you a demo of it, just so you get an idea of what it's all about. It looks at where the stars are relative to each other, and it does essentially massive geometric hashing and then some statistical pattern recognition, and it slaps you up on the sky. So it solves the sort of astrometry problem very, very accurately. And the nice thing about it is you don't need to give it an initial guess. So there are these systems like Pinpoint and stuff which will tweak up your image, your pointing for you. But here you can just, you don't need to tell it anything about where you are. So I'll show you, if we get up here, I'll show you a quick demo of it. Okay. So we've been using the astronomy picture of the day here as the test bed. So this is a site run by NASA, and they just, okay, thanks. They just post a different picture every day. So here's today's picture. I guess it's of one of Barnard's nebulas. So basically, I just need to grab this link here, and then I'll show you a demo of the service. So this is in collaboration with some astronomers at NYU, and so it's all in alpha testing now. But I'll just give you a quick demo of it. So basically, we're going to try and make this a service. Let me get rid of this and use a smaller version of it. They usually have a low-res version, which will. So you just need to tell it something about the scale of your image. So that thing is probably about 5 or 6 arc minutes in size. So maybe, I don't know, 6 times that or something. So I'll put in some estimate of how wide it is. This just speeds it up. If you give it a wide range or you give it no guess at all, it will just search all the scales. Anyway, so then it goes and it grabs that image off the web, and it does source extraction on the image. So you can see the red circles are where it found objects. And this is all very, very trivial computer vision. It's not doing any hardcore sub-pixel localization or anything. And then it cranks away on your image, and it looks for patterns of stars in the image that it recognizes, and then boom, it tells you where you are in the sky. So here you are. It tells you at the top the RA and deck of your field, and then it takes all the known stars from the USNO catalog and it reprojects them into your image. And then on the bottom, it actually gives you a WCS file. This is the astronomical, it's called World Coordinate System. So it's a very precise way of specifying your pointing and your tangential distortion. So the plan is to put up a service, for Google to put up a service where any amateur astronomer anywhere in the world can upload their image, and then we'll tell you exactly where on the sky your image, and if you check the box that says, yes, I volunteer to donate my image to a global database of astronomical observing, then we can lock the image down on the sky, and we can build a structured global observatory. Instead of just having people upload images with no information about where they are, we'll actually solve for the position of the image. And then because we know so much about the sky, we can actually back compute all kinds of things about the distortion of your camera and what bandpass you're looking in and everything. So we could get thousands of images cranking through this thing pretty soon. So if you want to help out, please send me an email. Lance. Yeah, so Lance is just asking me to point out the way we actually solve the image is we look for 4 stars that are, thanks Dick, we look for 4 stars that form a quadrilateral, and the exact angles of this quadrilateral are used as a geometric hash key into a huge database of millions of hash keys. And so as soon as we find 2 quads in the image, both of which hash to the same position and rotation in the sky, then we decide we think we have a pretty good hypothesis, and then we test the hypothesis. And the way we test the hypothesis is we shear and rotate your image according to the transformation implied by this, and we look for coincidences. So here you'll see there's a green circle and a red circle. That means there's a source in your image, that's the red, and a USNO object that lie exactly on top of each other after the transformation. And that happened like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, you know. It happened like 30 or 40 times in this image. So the chance of that happening by accident is, you know, 1 in several billion. So we just dial in a false positive rate of, you know, 10 to the minus 10 or something, and then we're absolutely sure that we know where you are on the sky. So yeah, so send me email if, or I guess Dick and Ben are going to put a link to that, so to the PDB page.